Today we're going to look at page 5 of the notes on unit vectors. And a unit vector is just a vector that's 1 unit long. So unit meaning 1. And we'll look at the little blurb that we talk about here in a moment. But let's look at just an example of what we would use a unit vector for, or when they would ever come up. Let's say I give you a vector in component or in rectangular form, -3, 2. So I can graph that vector. Here's my vector v, left 3, up 2. And vector v is definitely longer than 1 unit long, so it's not a unit vector. So if I want to make a unit vector that points in the same direction as v, however is only 1 unit long, we need to learn how to do that process. So we can definitely see that this vector v is longer than 1 unit long, as I said before. And Pythagorean theorem, we know how to determine the magnitude of the vector. That's right here. Now, if I want to find a vector that points in the same direction, however, is only 1 unit long, I want that vector to look something like this that I've drawn here. And I can do that very easily by taking my vector that I had previously, my v, and take the magnitude of the vector, the length of the vector, and divide my rectangular form vector by the square root of 13, or its magnitude. If I do that, it will result in this calculation. Take my vector, divide it by this scalar number, so it's just a magnitude, and that's going to take each of these x component and y components, and it's going to shorten them down. And when I have this calculation, we know how to rationalize that. So this is the exact value or exact length of the x component and the y component for our situation. Now if I divide and get a decimal approximation, I found that to be -0.83 and about 0.55. I can see a little bit better that this is in fact looking like it's going to be only approximately 1 unit long. If I go over left, -0.83, and up 0.55, I can see that it is pointing in the same direction as v, and it does appear to be only 1 unit long. Now next I showed the steps of actually finding the magnitude of this vector u, or the unit vector. I'm claiming it to be 1 unit long. And so if I want to determine that, we know that if we take the x component squared plus the y component squared, we'll determine the magnitude of this vector, and I found that in fact it is only 1 unit long. So if we want a vector to be turned into a unit vector, or to take a vector and find a unit vector that is pointing in the same direction as it, but is only 1 unit long, it's actually very easy to do. And that's what this is showing up here. Take the vector, divide it by the magnitude of the vector, and you'll actually change or find a new vector that will be pointing in the same direction, however, will only be 1 unit long. Now, we have a few notation for vectors at this point, and we know that rectangular and component form vectors, those two terms mean the same thing, and that's going to mean that I have the x component and the y component, the left-right movement, the vertical movement here, and we know how to change this into other forms as well in the previous pages. We know how to change this type of a vector in component form into a common or polar form. And remember, both cases, the common and the polar form, both have the magnitude of the vector here, and then we have the direction that the vector will point in. And remember, the only difference between these is what your reference point is. This references north. This basically references east. And this will always rotate clockwise, and this will rotate counterclockwise. So this is more of our traditional way of measuring angles, starting at the positive x-axis and then rotating in the counterclockwise direction, versus this is dealing with north as the reference point and rotating in the clockwise fashion. Now, there is another form of vector, the last form that we'll look at, that is another common notation for vectors. And that's if we write our vectors as a linear combination of 2 unit vectors. The first unit vector is unit vector I, and unit vector I is simply the vector 1, 0. I drew a little picture of it here. So if I put it in standard position, and started at the origin, it is only 1 unit long and it just points to the east. Unit vector j, and remember you can put the arrowheads on top of the vectors too, or just have them in bold, but unit vector j in its component form is 0, 1, and it points to the north and is only 1 unit long. Now every vector we have that's in component form in particular can be written as a linear combination of these two vectors. So if I had a vector v that was in component form or in rectangular form AB, then I can think of this as adding a whole bunch of I movements, AI movements, plus a whole bunch of J movements, B of those. So for instance, if I had the vector 2, 3, and I wanted to find the vector written not in component form, but as a linear combination of these two unit vectors, think about how I would do that. Well, I know I need to move 2 to the right, and that means I need to move I and another I. That's the first unit vector I, that's the second unit vector I. And then I would need to move 3 up. There's a vector j, another vector j, another vector j. So if I take 2 I vectors plus 3 j vectors, I'll actually have the same vector as this component form. So it's just a matter of writing it in a little bit different notation. When we use rectangular, component, common, or polar form, don't forget to put these arrowheads on the outside. We need those there to show that we have a vector. However, if we're writing our vector in a form that's a linear combination of vectors I and j, we don't put the little arrowheads on the outside. So that's used for all the other forms except for this. So this is showing that I'm adding a whole bunch of little vectors together, and there's no need for those pointy parentheses. Now I show a couple examples on the next page. We'll just quickly turn to that, and then the video will be done. All right, so on our first one, very easily, if I wanted to express vector 2, -7, which is in component or rectangular form right now, and want to write it as a linear combination of unit vectors I and j, it's this simple. Because remember, if I'm dealing with going to vector 2, 1, 2, 3, 4, 5, 6, 7, we know that in standard position this is that vector. But how would I get there? Well, I would have vector I plus another I, and then I would have a -j, etc., 7 negative j's that I would have to move to get down to that location. So 2i minus or plus -7j. Arrowheads can be put above those, just all depends on the text. Now, on the other hand, if I gave you a vector that is in polar form, we know that the length of the vector is 13, and its angle is 40 degrees. I actually have a little more work to do in order to write this vector as a linear combination of I and j. So I drew a picture of what this vector looks like, and we can see that I needed to move 40 degrees from my positive x-axis because my angle was given as a polar form angle, or in standard position, and I know it is 13 units out. So I really need to determine what this x and y component is, or basically convert it into a component form vector. And I can use my sine function to help me determine the y, opposite over hypotenuse. I got that to be a little over 8.3. And I can use my cosine function, cosine of 40 degrees, to help me find the x value. And I got that to be almost 10. So now I can write that as a linear combination. I know to move on my x position and then move up my y position. I can move out to this vector, and my x component is 9.96 units long. Therefore, I would need 9.96 i's to go in off in the easterly direction, and then I would have to go in my northerly direction 8.36J units. So there we are as a linear combination, and had I asked for component form, we would have written with the pointy parentheses the 9.96 and the 8.36. So again, you do not use the arrowheads at the end when we have the linear combination. These vectors being added together make it a vector. We would need the pointy parentheses or the two arrowheads if we are in component form, polar, or the common form. And that's it for this video.